Hello, denizens of the deep. Here we are. Today we're doing section 2.2, and that is infinite limits and limits at infinity. So today's lecture is going to be a little bit different, or I shouldn't say today. There's no today here, but I'm going to do the lecture on 2.2 a little bit differently than I did on 2.1. On 2.1, I kind of went through all the homework problems and kind of like taught it as we went along. And 2.2, I'm going to do it differently. I'm going to do it more by the book. So here we go. So we're going to talk about two new types of limits, infinite limits and limits at infinity. They sound similar, but they're not the same thing. Infinite limits and vertical asymptotes are used to describe the behavior of functions that are unbounded near x equals a. Now I'm going to show you what that means. Let us go here. And there, oops. Okay, here's a function. The red is a function. Let me make this invisible for a second. The red is a function. Y equals x plus 2 over x minus 2. It's a whatever. This thing is called hyperbole. You probably may not have seen it somewhere in your studies. This red thing. Now, if you notice, when x equals 1, it shoots up infinitely big, and it shoots down infinitely low. So this is what we so this green dotted line here is a vertical asymptote, and this is an infinite limit. This is an infinite limit. It means x is a finite value, x equals 1, but the function value shoots up to infinity. So this is what we call an infinite limit. Now, a limit at infinity is what happens when the x value becomes infinite. What happens to the function value? By the way, the function value and the y value is the same thing. So let me get rid of this one, bring this one back. Well, as the function goes out to infinity, the red graph gets closer and closer and closer to this horizontal line, y equals 1, and on this side also gets closer and closer to y equals 1. So this dotted line, y equals 1, that's the limit at infinity. It means as x becomes infinite, the limit of the function is 1. The limit of f of x is 1. And by the way, y and f of x are used interchangeably. When I say y or I say f of x, I'm using those two things interchangeably. Okay, let's go back to the textbook now. Okay, let's go on to the next page. So infinite limits. So if x approaches 1 from the positive direction, what's going to happen is see, if I let x equal 1, then you get 1 over 0. Now 1 over 0 is undefined. But what we're going to do here, instead of just saying, oh, it's undefined, we're going to see what happens to the function value, what happens to f of x when x gets close to 1. Now, this actually limit, now, okay, see, this is interesting. It says does not exist. I mean, it's infinite. Let's go look at the graph of that. Let's go back to Desmos. So let's just change. So what was it? Just 1 over x. What was it again? 1 over x minus 1. So I'm gonna go change this now. So these here become useless now. So if I look at x equals 1, x equals 1, that's the vertical asymptote. So as x approaches 1, now when it approaches from the positive direction, it goes up to positive infinity. Meaning there's no actual number. Infinity, by the way, is not a number. Infinity is a direction. It's you go towards infinity, but it's not something you ever actually reach. So just be clear about that. But that's what this looks like. Let's go back to where we were. Okay. Anyway, so we say, so there's no actual number because it gets bigger and bigger and bigger and bigger and bigger. I can't say that the limit is 100 because it gets big as I get closer to 1. It's bigger than 100. I can't say the limit is 1,000 because it gets bigger than 1,000. I can't say a million, a billion, or even a trillion because it gets bigger than that. So we just say infinity, even though infinity is not a number, but that's what I mean. anyways, so we're using infinity to describe the manner in which the limit fails to exist. I mean, it doesn't exist because it just gets super big and there's no number that it ever equals. It's bigger than any number you could come up with. They call that an infinite limit. That's called an infinite limit. And we use the infinity symbol, which is like a sideways 8. And again, so they drew a nice little graph picture for us right now. And pow, we have all these values here. So when x is 1, if x is 1.1, then y equals 10. If x is 1.01, y is 100. If x is, if x is 1.0001, then y is 1,000,000. And as x gets closer and closer to 1, this gets bigger and bigger and bigger. Now on the other side, if I approach from the negative direction, from the left-hand side, then the y value goes down to -1,000,000 or -1 billion or -1 trillion as I get closer and closer, to the number 1. So therefore, I would say that the limit as x approaches 1 from the positive direction is infinity. The limit as x approaches 1 from the negative direction is negative infinity. The overall limit does not exist because the only time the overall limit exists is when the left and the right are the same. So since one direction shoots me up this way and the other direction shoots me down that way, there's no overall limit because it doesn't, it doesn't agree with itself. Is that weird? Alrighty. So here they were saying construct a table. This is a nice exercise. Construct a table similar to what we have over here. It's a nice little exercise. Construct a table similar to this over here and see what you get. Now this is interesting because this actually will become, since I'm squaring it, it will become. In fact, let's go back to Desmos. Let's take a look at this. What I'm going to do is. And I'm going to this is interesting because since I'm squaring it, they both go up to positive infinity. So that's kind of interesting. And again, the asymptote is the same asymptote because all the infinite stuff happens when x equals 1. So that's kind of cool and interesting. All right, let's go back to where we were, kind of flipping back and forth there. Okay. Okay. Infinite limits. By the way, all this I'm showing you now, where did I get this from? This is all inside Math Excel. When you go to section 2, go to any problem in section 2.2 and click textbook pages, textbook, whatever, this is what you'll get. You'll get the textbook pages on the entire section 2.2. So what I have here, you can all get yourself. It's available, accessible to all of you with the Math Excel. All right, so infinite limits and vertical asymptotes. So if you have, well, this is really just reiterating what we said before. Let's go through the actual real stuff here. Locating a vertical asymptote, that's interesting. How do you locate a vertical asymptote? Like, I can never locate anything. How do you locate a vertical asymptote? Well, if f of x is equal to n of x over d of x, this is called a rational function because n is just like a rational number is a fraction. So a rational function is sort of a fraction. The numerator is some function, the denominator is some function. We're specifically looking, I believe, we're looking at polynomials, but not necessarily. Then the line x equals, so it's a rational function, d of c equals 0. Notice c is a value that if I plug in c for x, it equals 0. And the top does not equal 0. So the bottom becomes, if I would plug in x equals c, the bottom of this fraction will become 0. The top of the fraction will not become 0. Then x equals c is a vertical asymptote of the graph f. And we really did this before. We had a function before where if I plugged in x equals 1, the top is not 0, but the bottom becomes 0. We actually had 2 examples of that in the same video. Oh, I hope you all like my tie. There you go. So what can I say? I like certain things. So let's look at the vertical asymptote. Where did you leave it? So x squared plus x minus 2 over x squared minus 1. Well, if x equals, well, see, you could just say, well, if x equals 1, the bottom becomes 0, and if x equals -1, the bottom becomes 0. The thing is that I have to see if 1 or -1 make the top also equal to 0, because then it becomes a whole different ball game. So x squared plus, well, if I plug in x equals 1, I get 1 plus 1 minus 2. So if x equals 1, then the top also becomes 0. So I already have a different situation here. If x equals -1, then I have 1 minus 1 minus 2, which is not 0. That's -2 over 0. So if x is -1, that's definitely a vertical asymptote. If x is +1, it's a different story. But so what we're going to do here, we're going to factor the top. If we're able to, we're going to factor the top and we're going to factor the bottom. When we do that, when we factor the top and we factor the bottom, oh, we're not doing that here. Sorry about that. What we're doing here is we are what are we doing? We are plugging values in. We are plugging values in. And now let's look what happens if I would just take the top and factor it. I get x minus 1 over x minus 1 times x plus 2. That's what the numerator equals. The denominator, if I factor, is x minus 1 over x plus 1. Notice the x minus 1s cancel. So I now have, this is just x plus 2 over x plus 1. Well, if x equals +1, then this thing just equals 2. I'm sorry, it equals not positive, the 3 over, this just equals 3/2. If x equals -1, that's when it becomes infinite. So +1 will not be an asymptote, as you can see from this picture right here. +1 will not be an asymptote, but -1 will be an asymptote. But why did they put that little? Notice there's like a little open circle there. Why did they put that little open circle right there in the graph? The reason is because if I just can't, this is something you have to be very careful about in general. If I just cancel out the function, I have x plus 2 over x plus 1. So there's nothing wrong with putting in x equals 1. Nothing special about it. But this stripped down, pared down, function. That's not what my function equaled originally. Originally, my function was this guy. And this guy, if you plug in x equals 1, you do get 0 over 0, which is undefined. 0 over 0 is undefined. Therefore, I can never plug in x equals 1. But it doesn't shoot up to infinity. I just have this little hole in the graph. So what can I say? I have a very holy graph. Moving on. Let's find the vertical asymptotes here. X squared plus 20 over 5 times x minus 2 squared. Well, if you notice, x squared plus 20, that cannot be factored at all. You should know, we all know from algebra, there's no way you can factor the top. So really the question is, when is the bottom gonna become 0? Well, that's going to happen when x equals 2. So this is what the function is going to look like, and pow. So since the left-hand side and the right-hand side both equal positive infinity, even though this function is not really continuous, because these two curves, as they go up and up and up, they never meet. But that doesn't matter. There is a limit, and the limit is infinity. Because whether you come from the right side or whether you come from the left side, the function goes to infinity as I approach x equals 2. That is the story with that. Okay. Now I have now we're going to look at something which is kind of related, but not exactly the same thing. And that's limits at infinity, meaning when the x value, see, it says the limit is x approaches infinity. So as the x value gets bigger and bigger and bigger, or if the x value gets bigger and bigger negative, what happens to the y value at that point? And sometimes when the x value gets big, the y value gets big. Sometimes the x value gets big, the y value gets small. There's millions of possibilities here. So if I have, this is interesting, if I have y equals x squared, so when x becomes infinite, y becomes infinite. But if I have y equals 1 over x squared, then as x becomes infinite, y goes down to 0. course, when x approaches 0, y shoots up to infinity. But that's not what we're talking about right now. We're talking about the x value is the one that goes out towards infinity. When x goes out towards infinity, the y value gets closer and closer to 0. Very fascinating. So let's see if we got a x squared. Okay, let's move on. So the limits of power functions at infinity. If x is equal, so p is a positive real number. P is a positive real number, and k is any real number except 0. So when x goes to negative infinity, this becomes 0 because the k is just a constant; it stays the same. But when x gets bigger and bigger, x to the p power gets bigger and bigger and bigger. When on the other hand, when x goes to positive infinity, and look at number 2, when x goes to positive infinity, it's going to be the same thing. The top is going to stay the same, but the bottom here is going to get bigger, bigger, and bigger. It's going to become, very infinite. So the limit of that winds up being 0. Now, if I have if instead of as a fraction, I have k times x to the p, well, since x to the p is getting bigger and bigger and bigger, it's either gonna, be positive infinity or negative infinity, depending on what the, depending on the stuff. So depending on what p is actually, and or whatever. So so that's what's going to happen. And if I have k times if x goes to positive infinity, again, this guy is going to be positive infinity or negative infinity. And provided that x to p is a real number for negative values of x. And the limits in 3 and 4 will be either positive or infinity or negative infinity, depending on k and depending on p. That's just the way it is. So let's move on. Let's look at example 3, the limit of a polynomial function at infinity. So p of x is equal to 2x cubed minus x squared minus 7x plus 3. Oh boy, oh boy, oh boy. Now, find the limit of p of x as x approaches infinity and as x approaches negative infinity. Oh boy, this is, well, I'll tell you right now, this is, well, from algebra, we know, by the way, that when x approaches positive infinity, this is going to become positive infinity, will be the limit. And when x approaches negative infinity, this is going to be negative infinity because x to the third is an odd power. We actually kind of know that from algebra, but let's actually work it out step by step. So we're going to factor out 2x to the third from this guy right here. So it becomes 2x to the third times 1, because I divide 2x to the third by itself, I get 1, minus 1 over 2x minus 7 over 2x squared plus 3 over 2x cubed. Now, when x approaches infinity, that becomes 0, that becomes 0, and that becomes 0. So this whole thing is just going to be 1 minus 0 plus 1, which is equal to 1. So when x approaches infinity, this whole parenthesis here becomes 1, or becomes very close to 1. But there's more than that. There's also the 2x to the third. So what's going to happen is that p of x, which is 2x to the third times this whole parenthesis, it's going to be 2x to the third, roughly 2x to the third times 1, which is just 2x to the third. But when x becomes positively infinite, then 2x to the third is going to become positively infinite. So that's the so the limit is p of x as x approaches infinity is going to be equal to infinity. Now, similarly, I have 2x to the third power. Well, as x approaches negative infinity, 2x to the, because if x is, for example, if x is equal to 10, then this is going to be negative 2,000. If x is equal to 100, this is going to be negative, what's 100 squared? 1,000,000? Negative 10,000, negative 20,000, and so on and so forth. And it's going to become negative infinity. Okay, let's carry on. By the way, whenever it says matched problem, that just means it's giving you another problem of a similar nature. Alrighty, the term of the highest degree is called the leading term of a polynomial. This is something that you may have seen, probably have seen already in algebra. And so if P of X is some polynomial, A sub n minus 1, these are just the coefficients. So if P of X is equal to A sub n times x to the n power plus dot, 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 dot. So the limit as x goes to infinity of P of X is just going to be A sub n times x to the n, meaning all this other stuff becomes insignificant for the reasons we just showed above. And that's either going to be infinity or negative infinity, of course, depending on what A sub n is, and I guess and also what n is. And when x approaches negative infinity, then it's going to be it'll be the same thing. Alrighty, a polynomial A polynomial, by the way, notice here it says n is greater than or equal to 1. Oops. It says n is greater than or equal to 1. The reason it says that is because if n is equal to 0, then this whole polynomial is just a constant. And constants, there's nothing to, the limit of a constant is just that same constant. By the way, as x approaches infinity or negative infinity, there's a word for that you may have seen this in algebra. We call that end behavior. And if I'm looking at the graph, let's go back to graph. So if I have a graph here, end behavior means what happens at the end. So at this end, becomes 0, and at that end it becomes 0. It could be all kinds of wiggles and squiggles and crazy things happening in the middle, but end behavior just means I want to see what happens at one extreme end and what happens at the other extreme end. But that's the same thing as a limit at infinity. It's just two different ways of saying the same thing. Okay, one being a little bit, to me, one is a little more visual. And now if x approaches positive infinity, then we're talking about the right end behavior. If x approaches negative infinity, we're talking about the left end behavior. And these examples here, notice they all become infinite somehow. And here, in both cases, x becomes negative infinity. Now, how come in example B, whether x approached positive infinity or negative infinity, they both became, the limit was the same, negative infinity. But here in example A, the limit changed. One case was positive infinity, one case was negative infinity. The reason is because this was an odd power. The highest exponent is 3, x to the third power. So therefore it's an odd function, and odd function is going to wind up having a different, it's going to be positive on one side, negative on the other side. But this guy over here, the highest power is 4. So you see the 3x to the third. So you think, hey, it's x to the third, but it's sneaky. There's actually an x to the fourth right there. So the degree of this is really 4, and therefore it's going to be the same. Now, why is it negative infinity, not positive infinity? Well, really because that negative 500. That's really what does it. Okay, so let's move on. And now let's look at some practical examples. Sales analysis. By the way, I just want to take time out for a second and say that things like sales analysis, I just want to talk a little bit about how should I say this? It's the real world. So things like sales analysis, math is used a lot to analyze, if you're in a business, to analyze your sales, what's happening, you saw some patterns, what sells better, what sells worse. We're going to learn that we're going to use math to figure out the best price. Sometimes if you price something too high, you make less money because less people buy it. If you price something too low, you also make less money because people are hard. If you get away for free, then you're not going to make any money that way. So the calculus is going to help us find like sort of a sweet spot of how much to charge to make the most amount of money, and things like that. Math is used tremendous amount to analyze things, to predict what's going to, trends and things like that. So what I'm trying to say is like this: the more math you know, the more valuable you're going to be as an employee. Now, me, of course, I teach math in college, so of course I know math, and that's if I didn't know math, I'd be in big trouble. But let's say you have a job which is not, they're not looking for a mathematician, they're not looking for someone who knows math at all, but you happen to know math. It's gonna help you. It's gonna give you an edge. They're gonna know, oh, this is the one guy who knows math. makes you more valuable, makes you more useful, or it even makes you more attractive in a certain way. Uh, for example, one of my students took a lot of math classes. Actually majored in math. Got a job, was hired pretty quickly, and I mean, when I say pretty quickly, I'm talking about within like a couple of months of graduating college, like 1 or 2 months of graduating college, got a job. Now the job was you didn't really it wasn't actual math in the job. There was spreadsheets you had to do, but it was the title of the job was compliance officer. Compliance officer. But the fact that she was a math major, that actually made her more attractive to them. They just, for some reason, they thought she was, I don't know, more intelligent. I don't know what it was, or maybe, or they had a feeling someone who knows math can be useful. Whatever it is, that gave her a huge edge over the competition. So I'm just saying, the more math you take, now you don't necessarily have to major math. You can concentrate math. Just the more math you have on your transcript, the the more valuable you are. So that's just my plug. So speaking of math, let's actually do some math. Let's go back to the here. So this is sales analysis. So let's look at the case here. The total number of downloads, we're going to use the letter D for that, millions, of a new app, T months. So T represents time, or in this case, it means the number of months. After it is released, is given by this formula. D of T is equal to 3T squared over 2T squared plus 100. Now, how they came up with this formula, that's a whole other story. But I can tell you right now, there was a lot of math involved in making this, getting to this formula, which is also a huge demand. Businesses want these formulas because it helps them anticipate how successful a product is going to be, or you get the point. So the most important thing to know in business is the future. Nobody knows the future, but the better of a handle you can get on what's going to happen in the future, the better off you are. So find and interpret the limit as t goes to infinity of d of t. So here's the function 3t squared over 2t squared plus 100. So what we're going to do is we're going to factor out we're going to factor out 3t squared from the top and 2t squared from the bottom. So the top now, so this function is going to be 3t squared over 2t squared times 1, because when I pull a 3t squared out, I just get 1. Here I get 1 plus 100 over 2t squared. Well, when t goes to infinity, well, first of all, the t squared and t squared in this fraction here just disappear. That just becomes 3 over 2. Now, in this fraction over here, when t becomes infinite, I have 1 plus 100 over infinity, so to speak, which is basically 1 plus 0, which is just 1. So this whole thing becomes 3 over 2. But if you notice, when you do this enough, you're going to notice right away that 3 and that 2 is just going to be the final answer, assuming that they're both t squared and t, as soon as they match t squared versus t squared. Meaning if the powers are the same, highest power is the same, then the limit as x goes to infinity is just going to be the coefficient over that coefficient, 3 over 2. And we see that here, and we're going to notice that we're going to see that pattern more and more. Okay, let's look for some horizontal asymptotes. Well, horizontal asymptote, that's the limit as x goes to infinity. So in this case over here, the horizontal asymptote is the x-axis. What's the equation of the x-axis? That's y equals 0. Suppose I would, let's just, what happened if I did this? So that's one thing I like about Desmos. You could come up with weird functions. That's interesting. See, it sort of shifted a little bit. I made x plus 1, kind of shifted things. Let me get rid of the asymptote here. Kind of shifted things a little bit. It's kind of interesting. Anyway, but the horizontal asymptote is still 0. Even though this dips below the axis, but it's going to asymptote to the x-axis. This stays above, but it's going to asymptote to the above. Okay. Let's go back to the textbook. Let's see the examples. So horizontal asymptote. So in this case, we had, since we took the limit, we got 3 halves, because again, there's a 3x squared and a 2x squared, and the rest of it is just going to all go on vacation. I had a math teacher, instead of saying it canceled, he would say it goes on vacation. The 5x goes on vacation. Anyway, so therefore, y equals 3 over 2 is going to be the horizontal asymptote, because that's the limit. That's what we're saying here. Okay. And this here is a very, well, this is not, this is adding one little twist. Remember I said you could just look at the two coefficients if the degrees are the same. But what if they're not the same? So again, if they're the same, when m equals n, then I just take the top coefficient divided by the bottom coefficient of the highest power, and that's and y equals a over b, is going to be the asymptote. That's like in the example we just had a minute ago of 3 over 2. What if the top is a lower number? What if that's x to the 5th and this is x to the 7th? Well, in that case, it's always going to be y equals 0, because what's going to happen is that the bottom is going to become much bigger. A million to the 7th power is much bigger than a million to the 5th power, and a trillion is even a bigger difference, and there's whatever. But there's no number of zillion. I always thought a zillion was a number. It turns out a zillion is not a number. I never knew that. A zillion is kind of like an expression. It just means a huge amount. And the third case, if m is bigger than n, if the top is a bigger power than the bottom, well, what's going to happen is the top is going to, so if I have x to the 7th divided by x to the 5th, top is going to be way bigger. And this whole thing is either going to be positive infinity or negative infinity, depending on m and n and am and an, depending on all those different numbers, depending on what the numbers are. That's going to either be positive infinity or be negative. It's not going to be both. It's going to be one or the other. Alrighty. And this is an interesting function, because here it shoots up like that and it goes down. This goes down and goes up. They both have the same. They have it's just one horizontal asymptote. That's kind of interesting. Notice that in cases 1 and 2 of theorem 4, the limit is the same if x approaches positive and negative infinity. So a rational function can have at most one horizontal asymptote. So that's kind of cool. And finding the horizontal asymptote. So here I have third power. So it's just going to be y equals 5 over 4. Here I have 4th power over 6th power. So this one's going to be 0. Here I have 5th power over 3rd power. But since the 2 and the 6 are both positive, and then it's going to be positive infinity. Oh, I'm sorry. I should have said one more thing. Since the x to the 5th divided by x to the 3rd has a difference of 2, it's basically kind of going to be like the same as x squared. So therefore, it's going to be positive infinity on both sides. Let's look at the official. And here's the answer. So again, C is positive infinity. Notice that what they did is the limit of here is that when it gets super big, see, how can I just get rid of these other terms here? Well, because when it gets super big, the 2x to the 5th totally overshadows it. It's like this is an elephant and these are fleas. I'm saying this is a, this is like this guy here is like the state of Montana, and that guy there is like, not even a postage stamp. Saying it's like nothing. So it's x to the 5th over x to the 3rd, which becomes x squared. X squared is the same, as it go to infinity. It's going to be positive infinity in both ways. So which basically means no asymptote. Alrighty, let's look here. Now let's say you want to find the horizontal and the vertical. So for the horizontal, which one are we doing first here? So if the top is 2x squared minus 5, and the bottom is x squared plus 5x plus 4, which factors into x plus 1 times x plus 4. Now the top does not factor at all. So since the numerator is not 0 at x equals -1 or x equals -4, right? N of -1 and n of -4 is not 0. So by theorem 1, there are two vertical asymptotes, and that's going to be the line x equals -1 and x equals -4. Since the limit is x goes to infinity of f of x, and those are my vertical asymptotes right there. So I'm just looking at the bottom. All I'm doing here is I'm looking at the bottom. That's my strategy. I'm looking at the bottom. I'm seeing when the bottom equals 0, and I'm just checking that that value doesn't make the top equal 0 as well. Since -1 and -4 does not make the top equal to 0, so those are two vertical asymptotes. And as far as the other one, if this, well, it's just going to be 2 over 1 basically, because x squared is the same power, so it's going to be 2 over 1, which is what it says right here too. Let's just for fun, let's graph this. 2x squared minus 5. Let's see what it looks like. I'm curious. And that'll be it for this class, this lecture. 2x squared minus 5. X squared minus 5, and the other one was x plus 1. Was it x plus 1? So it's x squared plus 5x. So we have x equal. Let's look at x equals. Let's look at y equals 2. That's gonna be I don't want this in color. We'll fix that in a minute. And let's look at x equals. What was it? -2. And we'll look at x equals -4. Let's make that nice. So we're gonna make this apple is gonna be different colors. It's a nice color. Orange. And done. And now let's just make sky. Let's just make this one. So it's nice and tight. No, okay. So I'm gonna have to make this. I'm gonna shrink this so you can see. So x equals -4 is a vertical asymptote. X equals +1 is a vertical asymptote, and y equals +2 is a horizontal asymptote. So notice that there are two vertical asymptotes. There's only one horizontal. That's like the way it is. Now, we figured out in this example, we figured out the asymptotes. We didn't figure out what the graph looked like. We used Desmos for that. But we're going to learn in this class, using calculus, we could figure out pretty accurately what the graph itself looks like, and that's something we're going to get to. But that's just a little bit of a teaser. Anyway, it's been loads of fun, and that concludes section 2.2. And we'll see you guys next time. Bye, everybody.